Hello, good evening. Today I'm going to be talking about all the exciting new features in Apache Spark 2.0 and then some of the work that my group and others are doing within Oracle to kind of take it to the next level. My name is Brad Carlile. I'm Senior Director of a group we call Strategic Applications Engineering. And our group is focused on looking at a wide variety of different kind of applications with in Oracle, the whole ecosystem, and understanding its performance and how to drive things forward. We're especially interested in what's going on with Apache Spark, and I've done a lot of interesting work in that. Some of the things I'm going to be talking about today are kind of future-looking work in progress, and here's our safe harbor statement. A little about me. I started my career working in numerical analysis for a company here in Portland called Floating Point Systems, and then transitioned or was bought out by Cray Research, where we continued that work and started working with a lot of high-end Spark-based processors. Then we were acquired by Sun to do all of the high-end servers for Sun and eventually all of the servers. And then Oracle has, of course, acquired Sun, and we continue to do that. But more importantly, I like to ski. I like to travel the world and do all kinds of different things with that. Do a lot of climbing. I've climbed big walls, El Cap, and Half Dome. And I drive an art car. Although you won't see the art car today, my wife wanted to drive it today, so it's not outside. So a little bit about Spark. Spark is a very exciting project and product for us, but you already know that. That's why you're here. And I think one of the things that is really important to me is the whole ecosystem for analytics. Of course, all of the work that's being done to really make it a very efficient analytics products is very appealing to the performance expert in me. So we have a whole ecosystem for analytics. We can do things with selecting the data in Spark SQL. We have machine learning in MLlib, the work we can do with graph or streaming, and we'll talk about some of that. And even outside of Apache Spark are all of the other Spark projects around and other things that people are doing, Kafka, Solr for search, and so forth. So Spark is fast, and it has a very great and clean design to make it scalable. And it's also focused on in-memory, and that's particularly exciting to me because as memory of our systems keeps increasing, the more we can put in memory, the faster we can make it in memory. Memory bandwidth is, of course, much, much faster than what we can get on even flash. The other thing that's interesting is Spark speaks SQL. And data frames. And I'll talk a little bit more about that and how that'll help us make better systems in the future. And at the end, I'll tell you a little bit about, I have a couple slides on some of the interesting things we've done with putting some of the software into silicon and how that can be used with Apache Spark. Some of you may be wondering why Oracle, the big database company, is interested in Apache Spark. Well, it's actually quite clear. Not only the reasons for the top, but also a lot of Oracle's customers are using and deploying Apache Spark right now. So this is similar to the diagram you see a lot of people present on Apache Spark. I show it a little bit differently here. So I think of it as we all come into Apache Spark with whatever particular programming language we're working on. It could be Scala, Python, R, Java, what have you. And within that programming, we could be doing things to call into Spark SQL, either using SQL language or DSL. We could be calling into Spark MLlib to do machine learning or statistics, GraphX for graph, or Spark streaming. And having our analytics program really use any and all of these. And then, of course, what the data is now being stored on data frames and data sets. and we'll talk a little bit more about that. I know some of you who are using or started with the early versions, think a lot about RDDs. RDDs are still around, but with data frames and data sets, we also add the ability to put in typing into what we're doing and storing data in ways that we can make better use of it. RDDs are very general, and this gives us just a little bit more of a data structure design for analytics. And of course, all of this is on top of the Spark core. This does all of the operations that we need to make this happen. Now, one of the things that's interesting is the Spark core is implemented in Scala. Scala executes on the JVM. And I guess the thing that's interesting is, Oracle has a lot to do with Java, and we have a lot to do with making Java go faster. And of course, Java is a language that gets compiled and executed on the JVM. So things that we do to accelerate Java are really accelerating the JVM execution, and that, of course, then is leveraged to everything we do with Apache Spark. The other thing beyond all of the libraries or packages in Apache Spark is also all of the data sources that we have for analytics. Because if we look at what's going on, we could have data being stored or coming in JSON, CSV, could be stored on Cassandra or Elasticsearch or all kinds of things. And so that's a very valuable part of the Spark ecosystem. So today I'm going to be talking about some of the features that I find new and exciting with Apache Spark 2.0. This has just come out. I know talking to some of you earlier, you're not using Apache Spark 2.0, so I want to show you some of those features. It's got some great new features. First, I'm going to focus on Spark SQL. One of the great things now about Apache Spark 2.0 is it supports all of the SQL 2003 standards. So now we can really write SQL in the way we want to instead of kind of a subset, which made things more difficult. And in addition, Spark SQL can live on top of or get data from data frames and data sets, and that's become a unified new API. I'll talk a little bit more about that in a minute. Tungsten, phase 2. Tungsten is an optimization project within Apache Spark, and one of the things we do now to get more efficient execution is whole stage code generation, and I'll talk about that more in a minute. And then we'll get to these others later in the talk. So SQL. Some of you are probably thinking SQL, oh, you like SQL because it's for databases. Well, as it turns out, it's really the data scientist in me that really likes it, because SQL is a very powerful language to really express operations and get the data you want in a very concise and powerful way. We can sort data, filter it, manipulate it, and do all of those things. So yeah, as I just said, we can concisely express the data manipulation, and we can do it at scale. So this is not, oh, I have this little data set I'm doing on my laptop. I want to express how to loop over that bit of data. You can really, in the exact same specification, scale to if you had a 100 terabyte database or 10 terabytes of data. It's all the same way of specifying it. And we can use it for many, many different things. We can do our extract, transform, and load as we're taking data which may not be in the format we want to getting it into the format we want on a different system, cleaning up our data. We can use it to select the features we want to do analytics on within ML. We can create new features and generate them. So sometimes there's things in our data that we want to analyze, but may not be expressly in our data, but you can infer it from other data. Or there can be other kinds of things you can infer from your data. So that's creating a feature out of several features within your data set that may not be in the format you want. And of course, we can generate reports and get all kinds of interesting things from it. The other thing that's exciting about SQL is there's many well-known optimization techniques to optimize it. So we can take it in, you could write it in the way that makes sense to you, but then it can be transformed into a way that's executed very, very efficiently. So Apache Spark has what's called the Catalyst Optimizer. This is under the covers, you write SQL, and then when it comes to the execution, it's going to look at the operations you specified and possibly rearrange them into a different way to get faster execution. The other thing that's really cool about it is it's written to be extensible. So if your particular analytics that you're doing with SQL, and you look at it and you go, oh, that took a really long time to run. If they had done the operations in a different order, you can actually go into Apache Spark and write a new optimization and contribute it back to the community so other people can take advantage of it. I was just at the past 2 Apache Spark summits, and there's some really great work being done by many companies, and they're contributing those optimizations back in, which help everyone. So what does it look like? SQL, as I said, is a very simple way to express some powerful things. Here's a very simple example. This is the kind of example you can explain to your mother or your grandmother, right? I want to select first name, age, and gender from my customer table, database, whatever, where the age is greater than 20. And I want to order those results by age descending. Show me the results. It's a very simple way of doing it. I'll show you more complex examples in a minute, but this is the basic thing. So the other thing is it's got to operate on data. So how do we store that data? And of course, when we're doing transactions, the simple way to think about it is, say I have a customer and I store first name, last name, gender, and age. And then I have another customer. And so as I add customers, I'm adding all the information for each of those customers. And now the normal way to store this is, data stored row by row, if you will. But when we're doing analytics and when I analyze this, we're trying to analyze across our data. So actually it makes more sense to store it in a columnar format or think about it in a columnar format. So in my example, I just need to look at first name, age, and gender. I'm not trying to do an analysis of last name. So I might as well store my data contiguous in the columns because I'm analyzing across the columns. And we'll get into this a bit more. So I always think it's important not to reason from small examples, but think of more realistic examples. So one of the things that's happening and what we're trying to do is there's a lot of data about people that are out there, about transactions, and you want to capture all of that because you don't know which characteristics of your customers or their transactions or whatever that you're trying to improve. You may want to do analysis to say, who are my worst customers that I can make better customers? Or who are my best customers that I want to appreciate more or do something special for? How do I segment my customers so I do different marketing to different groups? So if we look at it, if we start looking at a customer, we could have, in a very simple form, we have, name, address, amount of money they spent with us, and we're done. But really, we're collecting more and more different characteristics that could have age, salary range, which loyalty plan they're on, what their marital status is, how many years they've been a customer, what's their favorite device for communicating with us, all number of different things. So we have a lot of data, a lot for each row of data. We have a lot of columns we could analyze. But for any particular analysis, we may only want to explore a small subset. So let's take advantage and make sure that we can access that small subset very, very quickly. So down here is just an example of not only can we store the data, But one thing that we can do with data frames is we can specify the type of the data. Is it a string? Is it an integer? Is it a floating point number? What have you. So here's some actual Scala code to specify the types of a variety of things in a column. Now the thing about this, as I mentioned, we can have lots and lots of columns, lots and lots of characteristics we're doing. Tens to hundreds are getting common. So we have lots and lots of data, but we may only need a small subset of that. So again, if we store the whole row and we put it in memory, you'd have to walk through each of these to get to the data that you want, or skip over it, or so forth. So we can do better, and I'll explain about that. So column store is going to be very important for us. Now, one of the other things I'm going to point out, because I've already had it in a couple of the examples, is there are a few changes to Spark 2.0.0. And I know this is tough to read. I'm posting these slides online. But I just wanted to put it here as reference. So there used to be a way that you would specify the SQL context and so forth. So there's a new way of doing it. It's called Spark Session. And really, that's what you want to move to. So just note that you want to move to Spark Session as you go to Spark 2.0. It's a little bit more concise way of doing it. And you can specify types a little bit easier. But the program is by and large the same. And there's a few other things you can do, and I put them here with Spark Session. Now you can look at all the tables within your storage, and you can list out what they are and get more detail. Again, this is mostly for reference. And this is from, there's more detail about Spark Session on the Databricks blog, so please look at that. So let's go back here. I've been talking about SQL, and some of you, may be Scala programmers or Python programmers and go, I don't really like SQL, that's old school. Well, that's fine. There's another way to specify it. That really is Spark SQL again. So here's an example. I want to select all the data, and I want to join the book authors where the author's year of birth is after 1980 and the first name is Paulo or something like that. And I want to order it by book title, right? So I can write that in SQL, or I can write it in what's called query DSL. And some of you may just think of this as writing in Scala or Python. Basically, in Scala, I want to create a data frame. I specify the author, the .join method, filter methods that I need, and then order by method. So it's basically the same thing in two different ways of specifying, whichever you're most comfortable with. Now, the thing that's really important about it is either programming style you come in, it goes into the Catalyst Optimizer. It will look at, should I filter for this operation or this one first? How do I do the join? How do I make it better? And then it just executes on that. The other thing you can have it do is you can actually have it show you what the plan looks like. So here's an example. So another query, I want to select from line order where the line order quantity is between 10 and 20. And I can see what comes on the output. Now, you may not need to do this if you're a data scientist, but when we're looking at how things are executing, trying to make sure they're more efficient, it's sometimes helpful to look at. So what you can do in Spark Session here, you can see the SQL and our query string is passed in, and you just put .explain on it. And out of that will come all of this. So we can see what data it's going after. You can see the between here in red with the quantities. I've stored the data off heap in memory. I can see I've done that and so forth. So it's a lot of detail, but again, I just wanted to point out in case you need to look at it. So the other thing that's new in Spark 2.0, and again, this is under the covers and just does the execution, or just occurs when you normally execute it, is whole stage code generation. So what this is doing is we're actually trying to have more efficient execution. And it's basically creating code to execute things directly. So to explain a bit, Apache Spark before 2.0, excuse me, used the volcano iterator method. So it's a very simplistic method. It's the way that when you're taught database execution in school, it's what you do. It's basically interpreted. So at runtime, it's going to open, it's going to get the data element. It's going to figure out which comparison you want to do at runtime, perform it, close it, then iterate. So it's very, very simplistic. So we can do better. In fact, as Reynolds Inn of Databricks, VP of Databricks Engineering, mentioned in one of his presentations, you know, a college freshman could write better Java code than interpreting it, because we can see it. And so tungsten whole stage code generation creates this pipeline code. You know, it's a simple loop. For line order quantity and line order, let's loop over it, and if it's between the values, let's make the count. So it's a very good way of, it's much better way of getting performance, and it has improved performance fairly dramatically. So it's one of the great reasons to move to Apache Spark 2.0. So this one's a little bit tough to see, but if you ever need to see it, I just wanted to give you the reference again. The slides will be posted so you can refer to them. But by appending in the front of the query string explain code gen, I can see what actual codes generate. And here's an example. So we can see exactly what's being declared and what things are going on. And again, this is really more for deep performance analysis, and you don't need it in your typical day. I want to go back and look at the whole analytics flow and what we're trying to do. So, you know, we have these different data sources. We could be streaming data in using Kafka or Storm. We could have data in various kinds of databases or multiple databases. We could have data in NoSQL. We could have things that we're getting out of search and so forth. So we have all of these pieces of data. And what we typically need to do is a lot of data munging, cleaning up, filtering, getting the stuff we need to do. And of course, for data scientists, unfortunately, a lot of time is trying to get the data into a form we can analyze. And then we do analysis, and then we get our results. So people often talk about the data pipeline. And I think it's actually, we can learn more by really understanding that it's not just a one pass through, that in fact we want to think about doing things differently. So I like to think of it in terms of an analytics cycle. So very simply, and I'll go into the details again, we have our data sources coming in. We're going to figure out which data we want to analyze. We're going to analyze it and get statistics on it and learn from it. We're going to get our results in a format we can use. And then we're going to keep doing that, right? Because we may find that we've analyzed one set of data, and we want to modify that and do it a different way. You've made a model, you've analyzed data for your European markets, and now you want to do the same for your American markets. So why should you have to start from scratch? And you don't need to. Or you're analyzing data and you've learned a little bit of something from it. You want to save that analysis because it's good and there may be some value for other analysis you want to do. Or it may point you in a different direction and you want to go over that same data again. So we go around the cycle and keep doing that. So say, for example, you have 10 terabytes of data you're doing. And in fact, there's cases now where even in the Oracle database, 10 terabytes of data can be compressed into 1 terabyte of memory, and we can operate in memory. And again, we can get a lot of advantages. And Apache Spark is very much the same. So we want to be able to do that. The other thing is, you'll notice I put SQL here. So here are the places where we're filtering and selecting and sorting data, and it actually occurs in many, many times. So it's not just I'm trying to select my data, but I'm extracting features, I can generate features, I can transform them, I can prepare things for the machine learning or graph, which is often very numerically intensive. I put FP here for floating point. But then we get numbers coming out of those algorithms, and I may want to turn it into something I can read or do something with, so then I use SQL again to do that. So I think it's very instructive to look at the whole analytics cycle. So I wanted to give you guys a quick example. Some of you may be familiar with the Kaggle challenges. It's basically for data scientists. Here's some data, here's a problem. How can you analyze and figure things out about it? So you can use it for training, for your learning by trying these examples and looking at what other people have posted. And then, of course, there's other data scientists who are trying to prove that they're kind of the best at their game. And so you can get involved with that. So here's one. I pulled this example from the Titanic challenge. It's basically given the passenger list and given their age, name, the cabin class that they were in, what their family structure was. Could you determine who survived and who didn't? And so here's an example in SQL, basically saying, okay, I'm going to take the passenger ID, whether they survived, the class that they were in, first, second, or third class cabin. I can look at their title, and I can rearrange the title and see if the title had anything to do with it, and put all of this, their age, whether they were with a family, they had siblings, mothers and fathers with kids or not, how much they paid, and I put all of this into machine learning, and I say, which are the aspects that help me predict survival rates, and so forth. So here it is in SQL, where I've created some features and I've filtered the features out. Here's the same thing written in Scala. I find SQL actually a little bit more powerful, a little more concise, but you can treat it in whichever way you want to. And of course, you could also code it in Python and so forth. Now, but the advantage, remember, is once I've specified it in either pure SQL or DSL, this gets optimized. This one, you had to write it in the right order. So again, I would encourage either using SQL or DSL to specify it instead of just writing code like you would. I think it can be made much more efficient. Here's another example of creating features. So for example, and again, this is mostly for reference. I know it's too small to read. But if I had something like a date in X, and how would I do something as I want to create a weekend flag? So I can do analysis and know if it occurred during a weekend, or if it's so many months to Christmas, right? Because if it's 2 months to Christmas, your buying patterns or your customers' buying patterns may change, or how many days to Christmas, or what season is it? So we can take things that are not expressly expressed in the data and create features that we want to do analysis on. So next, I'm going to be talking a little bit more about Spark MLlib, which is all of our machine learning and statistics, and also about GraphX, which is graph algorithms, for those of you who are not familiar with, are kind of the interrelationships between data. So I often think of a simple example of this is friends of friends in Facebook, right? You may want to do analysis to see who's connected to who by relationships and so forth. And there's some really powerful algorithms to help us understand and learn that. The other thing I'll note, in Apache Spark 2.0, there's actually 2 MLlibs, one that was written for RDDs, and then the new version is really optimized more around data frames because of this columnar nature of our data and the columnar nature of the machine learning we want to do. So really we want to move toward data frames. Again, you can take either, but all of the work's really going to be focused on the data frame API. So that's a transition you need to make. It's not difficult, and I think it'll actually help your development cycles because of the power of data frames and the type safety you can put in with data frames and data sets. The other thing that's really cool about Apache Spark 2.0 is the machine learning persistence. In machine learning, we typically are analyzing some data with known results, and then we're making predictions off that. And until we got to Apache Spark 2.0, you kind of had to, it only existed, the model only really existed during the stretch of your program. But now what we can do is we can save that model off to disk and we can reuse it, or we can move it to a different system and so forth. There's more on the Databricks blog, but I'll give you more of an example in a minute. Another great feature we don't have enough time to talk about today is structured streaming. In structured streaming, they've done some really nice things with it. So it's integrated with data frames and data sets, and one way I've heard of expressing it is you can do operations as if it was a fixed piece of data that you were analyzing. But you can, if you're working with data frames, you can think of it as an infinite data frame. So the classic example of streaming is looking at data from a Twitter feed. The data is coming in nonstop and we want to do analysis on it. What we can do is I want to say that here's the data frame as a Twitter stream that's coming in. But I don't know the end of it because I'm just doing continuous analysis. So we have all of the infrastructure in Apache Spark 2.0 to really make that a very powerful operation. So machine learning. Machine learning, and a lot of it's often different kinds of statistics as well. So we're trying to automatically sift through large amounts of data to find previously hidden patterns. We're going to discover, new insights and make predictions from it. So I put together several examples of kind of from a user point what you're trying to do and what some of the names are. So an example would be may want to identify the most important features. That's called attribute importance. So I'm trying to see what are the features that matter most to whatever I'm analyzing. Another one, you could be predicting customer behaviors by classifying different sets of customers. I could be trying to predict or estimate a value based on my data. So I'm doing a linear regression or a logistics regression through that. I could be segmenting my population into different groups. That's clustering. I could be trying to find fraudulent or rare events, anomaly detection, or determining co-occurring items in baskets, people who buy different sets of things. What are some of the interesting features of that? Do association analysis or decision trees as well. So again, the great thing about Apache Spark is that in MLlib, it has all of these different kinds of things where people have really optimized the algorithm. So as a user, you want to do logistics regression. It's basically calling the routines and it does all of that for you. And some really smart person has made that very, very efficient. So I want to talk a little bit about the two phases of machine learning, because oftentimes when you read, even in the academic literature, it's really focused around the interesting algorithm, which are here. But over here, this is the one that's really hard for systems. So let me explain. So in training or learning, I have a training set. I have a set of data that I'm analyzing with known outcomes. And I'm trying to see what are the features that all go together to predict the outcome. So this is where all the really interesting academic research is going, because this is figuring out cool, computationally intense algorithms. But what happens is I'm training, I'm learning from this training set, and I create a model. But then I have to use that model to predict or score all of my future data. And typically, this is huge amounts of data. Now, training or learning, and by the way, Spark calls it fit. So there's a .fit method to do the training and learning. And over here for the prediction or scoring, Spark has the .transform method. So you'll see that in your code. You won't really see prediction and training, but I think it's easier to understand. So for example, one of our customers is StubHub. And what they do is they're trying to predict ticket patterns and buying and so forth. So they have some really smart data scientists working on creating the model from all their customer data. And they do that on their desktop or powerful systems. Then they ship that model over to different systems in production and then evaluate nonstop huge amounts of data to improve their business and provide better information to the customers. So these are two different kinds of algorithms, and it's very important because these are very computationally intensive, a lot of floating point, but the prediction really is hard on system design because we have to move lots of data and we need lots of memory bandwidth in our systems. So in Apache Spark 2.0, as I mentioned, what we can do is we can train or fit a model. So in this example, there's a random forest classifier. It's written in Python. So you can see here, here's my, in this case, SQL context, where I get all my features and labels into my training data. I want to tell random forest that its parameters that I want to use. I want to have 20 trees when it builds its model. Here's my random forest that I'm using, and I'm fitting it to my training data, and I'm creating a model. Now, the new thing is we can take that model and save it to disk. So that's what we do during training. Now I can load it back in later to my program. So random forest classifier model load from disk that same model and reuse it. Now, this is an example in Python. As I mentioned, this could be on one system and this could be on a second system or systems. But I can also move it between languages. So I can create it in Python. Let's say my data scientists like using Python, and my production guys like using Scala. So again, I can load the model that was created in a different language on a different system, and then I can make my predictions. Now, not only can we do the numerical part of this, but all of the pipeline for creating the data, we can save that as well. So it's the whole machine learning pipeline. So a lot of great features there in Spark 2.0, but how can we make it even faster? And it can be made a lot faster. And I want to talk to you about some of the work and analysis that we've done to make that happen. So I want to step back for a minute, and I want to explore first principles thinking. And what I mean by that is, sometimes we think about things in a very simple way. And actually, if you really want to do better business, you need to look a little bit deeper. There's this great example from Fortune magazine that I came across last year. And it was talking about the Tesla Gigafactory. And what a lot of the pundits had been saying is, the reason they're located in Nevada is because of tax incentives there. Big businesses save, they can employ a lot of people within a state, so they try to give you tax incentives to move to their state. So conventional wisdom says the reason that the Tesla located their Gigafactory in Nevada was tax incentives. And for Apache Spark performance, we could think, I just need lots of cheap cores in the cloud, and I'm done. Let's think about that. When you're running a business, it's not just taxes that you're interested in, it's all the other things that contribute to the cost of your product. And if you're trying to make more product cheaply or increase your profits, you need to think about more things than that. So Nevada actually has great energy costs. Why? Well, the best geothermal in the continental US is near their factory. The sun, of course, burns brightly in Nevada with not very many cloudy days. In fact, this is how many kilowatt hours per kilowatt year in that corner of Nevada. In addition, they have generally high wind speeds, again, in that section of Nevada, so their energy costs are less. The other thing, the Gigafactory is using lithium as their raw material to make the batteries, the expensive part of it. The only lithium mine in the US is in Nevada. And in fact, lithium salts, which is kind of the new way of getting lithium, is also right there in Nevada. And they're only a few hours from the big markets in LA. So all of these reasons say that's why you want a factory there and not in some other place. So it's looking at all of the different factors. So when I apply that reasoning to Apache Spark, one of the things I've been mentioning, we have lots of data. If we're doing big data, we have to scan through lots of data, and it's going to be about delivered memory bandwidth. The other thing that's going to be very important is the JVM performance of Apache Spark. And then there's innovations we can do when we're scanning and filtering this data. So let's take an example of that. So let's look at the performance right now in Apache Spark 2.0 with whole stage code generation. So we took one of our servers, which is a 2-socket x86 Haswell system. It's got 36 cores total in the server, 18 cores per chip, 72 threads or vCPUs. And then let's look at the performance. So I'm trying to scan through lots of data. I did an example of a full table scan of 600 million rows of data. I came out with a time to scan of 0.16 seconds. Wow. You tell anyone you did something in 0.16 seconds and you think that's fast. You do the math and you say that's an impressive 104, almost 105 millions of rows per second per core. So I'm pretty happy with that result and I'm done. Well, let's look again. So going back to first principles, if I'm going through lots of data, scanning it, doing other operations, it's all about data movement. So what is the system bandwidth during this particular in-memory scan? 15 gigabytes per second. But what's the system capable of? 114 gigabytes per second. Actual measured delivered memory bandwidth. So if we're putting data in memory and trying to scan through memory, we could actually be 7.6 times faster. There's that much more bandwidth. And then we look at other queries, and in fact, we can be made much more efficient as well. So how do we get at this? The potential is there. How do we deliver? So let's go back to how SQL is executed. We look at it, the volcano iterator method, where we're interpreting data, the college freshman Java code, where we can express the loop. But you know we can do better than that, right? So how can we do better than a college freshman, or is that the extent of our coding? We can do better. We can have tuned libraries. When we look at lots and lots of SQL, it comes down to the same kinds of operations again and again, like a vector range filter, where we can specify the operation we want to do, the comparison values, the data, and we can have some really smart people spend a lot of time highly tuning this and making it very efficient. We can have the Catalyst optimizer just create this, because actually going back to the explain plan, it almost says this in the same way. Then the other thing we can do is we can do hardware acceleration to further accelerate our scanning. And so on x86, we have the AVX2, the graphics instructions. We can utilize them and achieve 70 gigabytes per second per chip. On the Oracle Spark processor, the M7 or S7, we can go even faster. I'll talk about that at the end. So one of the things that we've done is, where are we going to get this library of what the important operations are? So we actually at Oracle created a library we call libdax. DAX is for Data Accelerator. And we've made this open The API is open, and we put it out there for people to use. And we've designed it so it, of course, can be run on x86 or Spark or IBM Power, what have you. And we created this originally to accelerate SQL for the Oracle database in memory. And then all of this work can be applied to Apache Spark SQL. It's the same kinds of operations. And so one of the things we've done is not only made the API open, and by the way, you can go to this website and sign up, and you can try it on systems that we have. There's also examples there that show you how you could code it up in Python or Java. There's, I think, 10 or 15 examples of that. So we have x86 and Spark processor versions of this, and a generic version that'll be out soon. So this is a way of expressing these kinds of vector transformations. So that's about getting bandwidth, but what else can we do to make sure that we're making even faster than that? And there are things that we can do. So there's a variety of things. I've talked about the columnar format and vector processing. We can do operation pushdown. There's things we can do to accelerate join processing called Bloom filters. There's a paper that's referenced here at the bottom that'll go into exactly what these technologies are. And all of these can be brought to Apache Spark. And that's one of the things that Oracle we're trying to do to contribute back to the community to make sure that Spark just runs faster no matter what your platform is. So just as a reminder, the columnar format is really important. If I have these 4 columns of data, but I only want to look at this data, then let's store this data contiguous all together so I can access it and do operations without having to skip over all of these data elements. Now, Apache Spark has much of the machinery available to do this, but right now, columnar in memory only exists in a transitory state. We'd really like that persisted because that's the way that we really want to operate when we think about the whole analytics cycle. The other thing I wanted to talk a little bit about is some of the characteristics of the data. And if you're a data scientist, this is actually interesting, but as we're trying to make Apache Spark go faster, this is really critical to think about. So let's look at all the various characteristics we have. Season, there are 4 seasons. You know what? I don't need to store season as a fall, winter, spring, summer as characters. I only really need 2 bits to store it in. There's only 4 options. 2 to the 2 is 4. So I can encode that cardinality or that entropy in 2 bits. State, there's 50 US states. I only need 6 bits for that, and so forth. The other thing to think about is that most of the interesting data that we're going to be analyzing has fewer dictionary bits. So maybe I shouldn't be specifying these as strings. Maybe I should be encoding them, dictionary encoding them. And the other thing I'm trying to do is, I'm not trying to, when you're trying to segment customers or improve your work, you're not trying to look at a continuous value of things. You're trying to bucketize things. You're trying to see what customers within this range of, for example, salary. I could store salary as a dollar amount or a dollar and cents amount, or I could store it as ranges. How do people between $0 and $40,000 a year compare to people in their buying habits between people who make $100,000 and $120,000 and so forth. I don't need to know the exact values. I'm really looking for the ranges that give me different groupings. So in machine learning, we often bucketize. In fact, in Apache Spark, there are routines that will help, methods that will help us bucketize to reduce cardinality. So again, if I can store some of this data not as strings or floating point numbers, but in terms of numbers of bits, I can get a lot of compression out of this. So that's good to know. And it's actually important when if you're looking at data that's coming in, how many different kinds of data are represented in my stream. So cardinality is something to look at. But let's get to execution. I know not all of you guys are talking about, actually trying to make Apache Spark faster. You're just a user, but let me explain a bit. So here's a state list that I have, a chunk of data. And I have South Dakota, Tennessee, Utah, Texas, and so forth. Wouldn't it be better, instead of storing these long strings, that I create a dictionary for this segment of data? So any place you see South Dakota, I put a 0, Tennessee a 1, and so forth. So I've just done a simple substitution. I have a little dictionary here so I can translate forward and backward. Within this chunk of data, I can also store min and max. So if you had a query that said, oh, I'm looking for customers in Ohio, I don't even need to access this data. I've skipped that data. I've made my computation a lot faster. So in this example, South Dakota needs 12 characters, which is 24 Unicode bytes, 192 bits. But I can encode 50 states in 6 bits. So that's a huge compression. So now you can think about huge amounts of data on disk or streaming in actually being in memory because of this kind of thing. So right now, Apache Spark does have dictionary compression, but what they do is they use it to compress the data, then they uncompress the data, and then they do the execution on top of that. But in actuality, all I really need to do is look at these numbers. If I asked you to count how many customers are in Texas, you just go this one and this one, 2. Right? It's a very fast and simple operation. Now the other thing we can do to be clever computer scientists is we could say, you know what, I can compress this data. I can use zip or run length encoding, and I can get it down even further, more compression. So in fact, this is some of the things that we're trying to contribute back in to have a dictionary and then have the scanning work on an encoded dictionary, speeding up Apache Spark quite a bit. Now, as I mentioned, a lot of the framework is already there. We have, the Java objects stored in row format. There's clever encoders and decoders when we want to operate on compressed or off-heap memory and get many optimizations out of that. But right now, Apache Spark isn't persisting this, the columnar data. So we regenerate the columns each time, so it's on the fly, and then we get rid of it. So there are ways. There's a JIRA 15687 that talks about how we can persist this in memory, and we're trying to contribute to that as well. So to the developers in the audience, there's lots of great areas where you guys can really help make Apache Spark better for all of us. You guys, when you come up with creative new things, contribute the new algorithms into Apache Spark. Become part of the community. Another thing I'll mention that some of you may not be aware of, but if you go to sparkhub.databricks.com, Databricks has put together kind of an app store, if you will, for different kinds of things that people have come up with. So it's not part of the core Apache Spark, but they may be algorithms, or they may be various kinds of connectors to databases or other kinds of things that you can extract data off and bring it into Apache Spark and so forth. So there's a lot of different things that people are doing there. So look at that. You could save a lot of the work that you're doing by finding someone else who's already written that code and contributed it so you can see exactly what it looks like and use it, or you can contribute yourself. The other thing that I think is important is a lot of Apache Spark has been developed on laptops with few numbers of cores, or in Amazon Web Services with, again, few numbers of cores. But what's really happening in the hardware business is we're putting huge amounts of bandwidth together on single chips with lots of cores. So we need to take better advantage of that. So on x86, we can have 22 cores per chip now with Broadwell. The Spark processor has 32 cores per chip and huge amounts of bandwidth. So we need to scale up our executors to use lots and lots of cores within a chip before we think about going outside of that. Another piece that we're cleaning up is there's some misalignments. There's some 4-bit ints in front of strings that cause cache misalignments and slow things down. In fact, we're contributing to improving that as well. So Spark is pretty exciting, as I've been talking about. Hopefully you've been understanding that. I think it's a great ecosystem. It's fast and scalable because of its clean design. We really focus on in-memory. But Spark can be made much faster, as I've told you about. So there's innovations we can do in software. And I want to spend just 3 slides talking about some of the things we're actually doing in hardware to make it faster. So again, keep using, contributing, and sharing. We're trying to do that as well. So let me, again, get to those 3 slides. So those of you who know the history of Sun Microsystems, we used to make Spark processors. We still do as we became part of Oracle. Here's the Spark M7 chip up in the corner. That's a 32-core chip. And so with 32 cores at 4.1 gigahertz, we can have half a terabyte of memory per chip. So we can make very large memory systems. Again, in-memory is going to be important. We have huge amounts of bandwidth. A single chip has up to 160 gigabytes per second of memory bandwidth that we can have. So how do we do on performance? I mean, why do you want to make a chip? Well, you want to make a chip if you can make significant difference in performance. And with the design that we're using, the Spark processor core can be 1.6 to 2x faster than x86. That's a significant difference. I have database performance, and in blue I have megabytes per second. And all of these are done on a per core basis. So I've plotted them out with actual data that we've measured on both, looking at Sandy Bridge, Ivy Bridge, Haswell, and Broadwell, as well as from the Spark T5, M7, and S7. And so what we find is we've actually been making a very serious design effort in our cores to improve the per core performance with each generation. And of course, we're putting more cores per chip. So this is part of the reason we see the Spark processor doing a lot more performance per chip. But it's really the per core efficiency that we've been growing that's a lot of our performance. So in addition to that, the other thing we did was for the Oracle database, and which will also help Apache Spark, is we've taken a bunch of the things to do queries and basically put accelerators specifically on the chip to make them even faster. And I mentioned decompression here because as we dictionary encode, I said, well, we can do further compression. And so we've added that innovation so we can decompress and do the query all at the same time without creating extra data movement. In addition, we've added things to do hardware accelerated encryption, where we're 4 to 10 times faster than x86 because security is really an increasing thing in the world. And we've also added feature we call silicon secured memory. And what this does is it allows us to make sure that any of our memory references are really where they should be to protect programmer errors or to prevent things such as heartbleed, where you can read past beyond where you're trying to go. So if there's some kind of an attack or something. So you can read more about that online at Oracle's website. So I want to go back to first principles thinking and tell you a little bit more about bandwidth. So one of Databricks engineers is Patrick Wendell, and he was doing an O'Reilly data show with Ben Lorica, and you can go listen to them, and I often enjoy listening to them. And one of the things he said caught my attention. He said, no matter how high performance my engine is, if I need to scan a terabyte of data to answer my query, it's going to be slow, even if you are reading from memory. So let's look at that. So let's say we have 1 terabyte of in-memory and I want to scan it in 1 second. Well, how many VMs do I need, for example, in Amazon Web Services and AWS? The C4 8X Large is their highest performance compute engine. We can determine the memory bandwidth here. You can see on the link in orange and see the actual delivered memory bandwidth is 33.6 gigabytes per second. And if I want to scan 1 terabyte in 1 second, that means I've got to, if I divide that out, that means I need 31 of these VMs. That's a total of 62 chips. So how does that work on the Spark processor? So one of the servers we make is a Spark M7-8. So that's 8 chips in a server. We have delivered memory bandwidth of 1.2 terabytes per second. So I can do that kind of query. I have the bandwidth to do it in 1 second. And that all exists in 10 rack units, about a third of a rack. And 31, I'm assuming here, I don't know the exact size, but it's probably about 3 times larger than that. So we can do it faster and more efficiently, only using 8 chips, which conserves power and so forth, can reduce our cost quite a bit. So these diagrams down here, what I've done is I've put 1 circle for each of the processors. And how we design systems is we attach a certain portion of our memory to each of the processors. And then we have the interconnect and all of the logic to make it look like shared memory. So if this processor is accessing memory from this that's directly connected to this processor, it's got to interconnect to go over. Now in the Spark M7, we fully connect all of our processors in an M7-8, and I've drawn the lines in proportion to the bandwidth that is of this length. So again, if this processor needs something from here, that's the connection it uses. So it's fully connected. In the IBM Power 8, here's 8 processors. They have a different kind of an interconnect with less bandwidth. This is the 8-chip Haswell. Again, a different kind, not the same amount of bandwidth. So some of you may be saying, well, if I have 4 two-ways connected with 10 gig Ethernet, that's a good high-speed cluster. Well, in fact, I've also shown a fully connected, as we often connect networks fully connected on this. But at 10 gigabits per second, that's 1 gigabyte per second, as you can see, the lines are almost difficult to see here. So if you're running complex things within a node, you really want to do this kind of thing. And again, you can cluster these out as well. And we think that's the way to do it. The other thing, as I mentioned, with these SQL vector kernels, we've actually taken them and not just executing them in software in optimized library calls to do them. We've actually put it into silicon. So the DAX, the data accelerator, we took 1% of the chip to do these operations directly. And it's offload. And what I mean by that is, as the core is going along and says, I need to do this decompression to predicate scan, it hands that operation off to the DAX, which just goes off and does it. Using all of the memory bandwidth, the core can go ahead and do other computations because there's more to do than just scanning data. And so we can really get some benefit here from the offload. On x86, this same kind of functions are implemented with AVX2. These are SIMD instructions that are part of each core. So when we're doing the same operation, we're 100% utilizing all of the cores. And of course, we have less memory bandwidth per chip and per core, as I've shown you. So in the Oracle database, we're actually doing queries of timing in memory in the database, and we're 10x faster per chip than x86. So it really is a pretty dramatic benefit. And as I like to say, it's more important of how you use the transistor than the number of transistors you make. So we're really trying to do some creative things in hardware to really accelerate analytics of all kinds. And again, our customers are doing a wide variety of different things. This is not about trying to get things to the Oracle database. We have big customers who are using the Oracle database for their transactions, but they're also using lots of Apache Spark to do all kinds of data analysis and combining them together. So we really want that whole ecosystem to run well. And so we put some innovations into the hardware. We're trying to drive some more innovations back into Apache Spark software and so forth. Before we get to questions, I want to thank everyone for coming. I appreciate your time. I think Apache Spark's very exciting. I have a bunch of engineers in my group who are focused on Apache Spark and contributing back to the community and doing other work, and you hear more about that from us in terms of both x86 and Spark.